Okay, welcome back. So it's a pleasure to announce the second talk of Xinwen Zhu on the categorical local Langlands.
Okay, thanks. So I'll continue about the categorical local Langlands. So last time we said give you some kind of preliminary forms of categorical local Langlands. Says the category of smooth representations of, let's say, quasi-split periodic groups should be embedded into the categorical coherent shifts on the stack of L parameters. But also, even in the case of a torus GM, which is not, it shouldn't be of equivalence to categories. You are missing, just if you just consider the representations, you won't hit all the full subcat, the whole category. So today, at least I want to talk about, see how to the necessary ingredients to like make this conjectural what's going to be the equivalence categories, and then maybe at the end I'll give at least some examples, some kind of coherent shift on the stack which do not come from representations. Okay. So let's recall, maybe the first thing I want to talk a little bit about is VG. It was never explicitly mentioned, although or appeared some way. So let's first recall this. Okay. So again, this G is a reductive group over some field F. I guess last time I denote by F, but it was so. Okay, let me denote by F because E has like was in some lectures this was like a periodic field, but like in Eva's lecture it's like a ring of integers. So let's just do F, and then there's because we have it was mentioned there's like a tensor exact functor from and then maybe and let's see if S is some perfectoid space over FQ or maybe FQ bar, P bar. Then there's a tensor exact functor from the category of F isocrystals F over F to the category vector bundles on this Parks-Fontaine curve X given by, and then there's like a complete class. This is semi-simple abelian category has a complete classification given by slopes and give you a vector bundle here, which is the O lambda, which not necessarily rank 1, but now if you have a representation, then you can compose this functor with the category algebraic representations of G over F, and given any tensor functor. So by definition, a G isocrystal over F is by definition a tensor functor. Just here, okay, and then we have the let's say bound G XS is basically a tensor functor from here to, it's basically a tensor functor from rep of G now to the vector bundles, category vector bundles over F. And because of this by composition, we get just naturally a functor of groupoids of between groups. Okay, and then it's a non-trivial theorem. This I think probably in this. For arbitrary G, probably due to this should be due to Parks. it says that if you just consider the groupoid of isocrystals, G isocrystals modulo equivalence, this is a bijection to the groupoid of bond G C up to equivalence for C, some algebraic closed field, perfect toy field. For any. And then the set of isomorphism classes you should denote by EG. Okay. So yeah, maybe yeah, maybe there's some explicit description of this. I mean, there's some sort of it's just in the case of vector bundle, the usual just the F isocrystals. It's kind of easy to describe this set explicitly. So it can also be described as follows. You take this. It's just a. Okay, so this is basically what it is. It's a really G torsor over spec of F brave. F brave is a completion of maximum unramified extension of F together equipped with a forbidden semi-linear automorphism. But by Steinberg theorem, every G bundle over F brave is can be trivialized. So after you choose a trivialization, such sigma linear forbidden linear automorphism is just given by an element in the group, but then you need to mod out the equivalence. So where this equivalence is G and the H inverse G sigma H. These are equivalent. So the sigma is just a Frobenius. Or maybe not. Right. And right, so let me just remind you, like in Eva's talk, she mentioned there's sort of a complete combinatoric way to describe this set. So basically there are two maps. One is called Newton map, one is called the Cartwright map. It maps this set injectively to the following thing. You first take the times I1 G of gamma, where gamma is a absolute Galois group of F. Here I've sort of fixed a maximum torus, let's say abstract Gaudin of G, and its Covey lattice taking the rational span, taking the gamma invariance, and take the dominant part. So this is injective, and so then there's a natural partial order given. So and also there's a I think in Eva's talk she mentioned some kind of partial order if B less than or equal to B prime. If this is so-called the Newton co-character of B, and this the Newton co-character of B is less than or equal to Newton co-character of B prime, and they have the same Cartwright image. So here, this is basically means the difference is a positive sum, is a sum of positive rational rational positive is Q greater than or equal to 0 sum of positive co-roots. This is and minimal. So this gives this set a partial order coming from the partial order here, and one can show this minimal element in B of G are called the basic elements, BG basic, with respect to, let's say, this partial order. It's called the basic element, and then by this Cotton-Weight map, actually it's one-to-one bijective to pi 1 of gamma. Okay. Another thing I want to say, recall is this also in Eva's talk is if you give an element B in BG, now as I said concretely, it's just this G Bravo modulo some equivalence class. Okay, so let's say I lift B into an element here, then I can define J of B as an algebraic group over F. It's a F algebraic group. So it's a which I describe its functional point is in the F commutative F algebra. See, to groups which sends a ring A to elements G in G of A tensor F brave, such that the okay, that's fine. G inverse B sigma G is B. So this is so-called the twisted centralizer, where this forbidden sigma is really just on F bravo. Right? Okay. I mean, if you take algebraic closure, it's different description of F isocrystals. Yeah, this is like a more convenient way to. Okay, so see, from the definition, JV of F is going to be a subgroup inside here. Yeah, this is by definition. And this is actually a p-adic group. So in fact, is if JB, if B is basic, then actually JB is a form of G, meaning after this is a group over F, then passing to the algebraic closure, it should be isomorphic to G. Okay, and in general, JB is a form. Or maybe let me just say like not. So let me write this. JB, when you pass to base change to the algebraic closure, is a levy of F space change to algebraic closure. Okay. So so in fact here the JB is isomorphic to when you pass to algebraic closure is isomorphic to G. So these are actually basically it's called the elements here or such JB is usually called the extended pure inner forms. They're called so oops. Extended pure inner form. The reason is actually this set naturally contains the set of the set of Galois cohomology of G with coefficient. Yeah, this Galois set. I mean the set of G totals over F. Okay, and it's actually easy to see. There's a sort of the category of G totals is contained in the category of G F isocrystals because those are just those functors from rep actually factors to the category of vector spaces over F. Yeah, categorical vector spaces is sort of a Tanakin. It's a tensor subcategory of category of F isocrystals over F. So to get this. Okay, so this is something. Keep it here.
Or you said XS is part of it.
Huh?
X is part of it.
XS is the first something curve. Yes, was okay. Right now, so now we can define the following thing. Let me just see. We'll consider some sort of then. So maybe before going to the real geometric picture, let me just see. Just here, come back. Let me see a few words here. If you really think about it, both these are not just the. I mean, here I take the have bijection of sets, but this is really, by definition, these are groupoids. Namely, you can consider the category of such tensor functors with automorphisms. And as groupoid here, it's sort of the situation is pretty. Because of this, you can really think about this. This groupoid is a disjoint union of B in BG of like for each object, it's modulo. I mean the automorphism. So it's sort of a B of JB F, something like that, union. Or maybe let me write it in this way, more geometry. Okay. Of course, this groupoid is much more complicated to describe, and I won't really try to describe it explicitly here. But anyway, it's if you just look at the points, like the C points, they say S, if S is really a perfectoid field, it's also something like that. But maybe I just take the groupoids. Let's see. I don't know what's the notation usually to denote the groupoids. Or maybe just this. This is, yeah, this is a groupoid. This is sort of this, okay, point destroys, because this bijection point is still destroying union over B over BG element. But now it's basically taking the automorphism of objects here. But I mean, it was, as we saw before, this functor is actually not fully feasible, so they have different automorphism. So, but anyway, I can write it. This is point of modular automorphism. I guess this denoted by J tilde B. So if I have some B, you get the particular G bundle EB, and then this G tilde B is going to be automorphism of EB, which okay, it exists as some group objects in the, let's say, in the category of we would say okay, in this case it's a group object, at least in the category of pre-shifts on the category of perfectoid spaces. Okay, yeah, but anyway, the idea is if we just from the usual, now the basic idea is maybe I should say, when we talk, if I have a, let's say if I have a finite group G, you can think about the category of representation of G as a category of shifts on, if I have a finite group H, then the category of representation of H is going to be shifts on this classifying stack point mod H. Okay, and it turns out this idea is instead of considering category of like a smooth representations of periodic group G, or like you just consider the shifts on this kind of objects, and somehow this should give you this gives you a way to organize all these different category representations together. So let me try to make, and that category is, it turns out to be supposed to be equivalent to the category coherent shifts on the stack of L parameters. So let me try to make this precise. So we consider, let me consider the following thing. We say, just to, I give a sort of very formal definition, the quickest definition, but it won't give you much property of it, but it's at least the definition is it's most convenient way to define things. So we define definition a maybe pre-stack over, let's see, category perfect toy spaces over, let me just do FP bar is by definition is simple. To avoid some third issue, let me just add this adjective. You can safely ignore it. It's an accessible functor from, maybe over here, It's an accessible functor from the category perfect toy spaces over, maybe let me even add the affinoid perfect toy, maybe just what's okay, let's just do this to the category of groupoid. Okay, so and everything up here in this geometric content will be a pre-stack. So to just give you some example. Yeah, because I usually want to consider just the affinoid perfect rings, the Hooper pairs. But let's write in this way. Exam Bang G, which is such thing, you attach S to be the groupoids of G bundles on the Folksman curve. Point modification hasn't appeared yet. Yes, in her story, yeah, okay, I can do. Okay, yeah, in her story, when she defined like the spatial fiber of like this G Stuka, she basically considered like this G of isomorphism class is actually classified G of F Bravo modulo like some adjoint forbidden conjugation by G of O Bravo ring integers inside here, just using the same equivalence relation, and that is a set of isomorphism classes. It's her. So then there's of course natural map, and just I didn't. I say it's a sort of the automorphism of this. Yes. Yeah. Okay. Oh, this is like this what's called the local G Stuka over just F cube. Such called. I think she local G Stuka in Eva's talk over FQ bar or something like that. This is what the hurt. Yeah, this is you should. This is people. This is called like F iso crystal, and then you can like then you map to this new is usually called like get to the Newton polygon or something like that. Yeah, like for GON, this second information is actually already to pi 1 of G is already contained in the first information. But in general, you need a little bit more. Okay, so this is one of the main example. You can also, for every B, you can define the following thing. So you define this is a subgroupoid in bang of G such that you send S to those G bundles on here, such that fiber-wise, you restrict to over all the geometric fiber of S. For S is, let's see, some points, some geometric points. Every, or maybe it's just like any geometric points of this perfect for S, space S. This one is isomorphic to this E of B. Okay. Because we said over a field, the isomorphism classes of this groupoid is never change. It's given by this BG. So for every B, I can define this. And then this is apparently subgroupoid. You can also define something in between. For example, you can find bound G less than or equal to B to be just the similar thing. But you want this this ES is isomorphic to EB prime for some B prime less than or equal to, less than or equal to 2. Okay. So these are, okay, this is I make a definition and then give you the main examples. Yeah, and of course, like all this previously, all these diamond V shapes, they are all, belongs to the subcategory of this. This is the most general thing you could work with. Yeah. Yes, you maybe for any S there exists B prime. Writing this way. Yeah. Oh. Okay. Now let me try to say a little bit about. So these are defined as pre-stacks. They are actually proved to be V stacks, but I don't really need that. What I only need is the following thing. So maybe just state this fact or theorem. This inclusion is open. Meaning if you map any perfect space map to it, do the base change, you get the open subspaces. This first one. The second, for each B, actually geometrically it has only 1 point, basically because of this of what was mentioned there. But it has non-trivial automorphism. And this is literally point modulo this J of B. Now it stacks, and this J B tilde. Now it's automorphism of EB. It's really, it's really a functor from sense S to automorphism of EB. I don't know, I should write S or not, but this functor is really come from the first one. For each element in B, you do not just get a vector bundle on a point, but this really you have some family, something like that. Okay, and again, this is it's sort of some. If you think about this, like a case of vector bundles, we talk about like the endomorphism, which is like a Banach-Comet space is sort of some subspace of it. Okay, and so it's sort of presentable by like as soon as you base change to a perfect field, it's represented by a diamond. What else? And then this guy also has so because this is not fully feasible, so this is different from JB, but it has now I get confused. A priori, there's a map from JBF map to it, but I guess it also has a quotient to this constant. Yes. This is on here. It's inside here. EB is really just yeah, actually this is some phantom thing. If you don't, you can think about this is like for every S, you could just okay. Let me just write this as some formal notion. Yeah, but it's defined in this way. Let's see. Huh? This one. You are talking about this one. Yeah, this is exactly what I said. We have this functor for any perfect space S. We have this tensor functor, right? So if I have B, which is given by tensor functor, this then can be composed. Yeah. Okay. So right. All right. Okay. So that's something minimal thing I need. So in particular, this guy mapped to here. It's going to be mapped to point modulo JBF. You consider this is JBF is a per finite group, then you can think about it as make a constant whatever perfectoid like V shape, make the quotient. Huh? Yes. When B basic. It's basic. This is isomorphism. But not the case in general, if B is not basic. In fact, there's a kernel which is kind of some unipotent thing, has some whose dimension can be computed. Yes, so okay, let's keep this. Right, it's already. All right. So now, you mean the from map between the different disjoint union? Yeah, this is it's a groupoid. It's this. Yes. A map. I mean this. Yeah, there's a map both direction, I think. Okay. So now, we'll trying to define some category of shifts. So there's this general formalism to produce category of shifts. So on this perfectoid spaces, then there's this theory of L-lattice shifts. Let's fix lambda as some, let's say, L torsion ring. Some like Zima L to the N algebra for some L not equal to P, of course, and some N. Okay, I was advised not to talk about QL situation. So then there's let me write in this. This is in modern form. The quick formulation is there's a way to attach every perfectile space its category for étale shifts. With lambda coefficient, and I regarded this as a lambda linear whatever. Okay, for what I'm going to say, I really want to consider this is a lambda linear, let's say stable infinite categories. But as a first approximation, it's just a derived category for étale shifts. Maybe you need to. I think it won't be matter when talk about the shifts on Bang-G, but let's follow Peter's notes to write this is like kind of some left completion, some kind of the usual category of étale shift. Because this étale side on perfectile space is well defined and have this such thing. And then this is actually a counter. You can think about this theory attach perfectile space to such category as a contravariant functor, and with the translation maps given by upper stop pullback. This like come from this very general topos theory. You can do this, and then by Yoneda, this actually embeds into the category of pre-stacks. Let's see over FQ bar. Let's just do everything over FQ bar. And then there's a general procedure. Once you have such functor, there's always general procedure allows you to extend this to factor through here. This is so-called the right Kang extension. Gives us you a functor, maybe to any pre-stack over F. You can attach to lambda linear stable presentable infinite categories, and then for explicit formula, if for such X, you attach Px, and the formula is given by you take just the inverse limit of all ds lambda for S is a perfectly space mapped to X. Like that. Of course, there's some set theoretical issue because there's just too many, but that's the reason I added this so-called accessible functor. So you really only need to take the limit over some set of such things. Okay. Lambda is some coefficient ring. Let's see, Zima L to the N algebra for some algebra. Yeah, it's a little smooth. Yeah, sorry. Okay, should be a little bit fast. Right, the Kang extension takes the limit. Yeah. Oh yeah, but sorry, because yeah, it's right. Yes, maybe. Yeah, I think that's okay. It's a right adjoint functor. Okay, so a definition as such is really general. So for general pre-stack, you really can't say anything about such category, although you can define it. But surprisingly, for Bang-G, it's really good. So this is summarized to this theorem. So first, this is the debunk G lambda is compactly generated. Yeah, maybe before go to, let's first start from one strata. Actually, it's equivalent to your point modulo JB F. And as I explained the basic idea, this category of shifts should be basically equivalent to category of smooth representation, derive the category of smooth representations with lambda coefficient. Second, this is compactly generated. So in general, without the, you can define some category, but without knowing compact generation, you basically can't say anything about it because you don't know how to do computations. But fortunately, this is compact generated with an object A inside here compact if and only if its restriction of this guy to any strata is compact. Yeah, by the way, I should see, because I have this map here, so I also have this bound GB inside here. So the composition is denoted by IB, this locally close embedding, and it's sort of built in this definition that for any map you have a pullback of shifts. So this guy is defined using this machinery. This is compact for every B and 0 for almost all B. That's it vanishes. It's basically supported on the finite meaning, strata. So this is yeah, and 3 as probably I don't need it, but I'd like to see this as a compact there's a general notion of duality of linear categories. If it's compactly generated, it's automatically dualizable. It has a dual, but in this case, it's self-dual. Okay. And then there's a canonical self-dual, and this was called the Bernstein-Zibinski duality. Yes, for almost all B's. It's this is compact for every B. But then yeah, that's probably bad English, but the 4, what I want to say, I think I want to say one more. Yeah, and then so this upper star admits actually both left and right adjoints. It admits right adjoint is basically because it's in the compact to compact. When I say adjoints, I mean continuous, right? And I guess there's also left lower Schraik. And then because all these adjoints are continuous, this gives a so-called semi-orthogonal decomposition. This is a semi-orthogonal decomposition of this debunk G by all these various category of representations something, which basically means I don't have time to go to the details, but it basically says this whole category is glued from various of these small categories. That's a representation category together. If you want, the compact objects are also glued together. And then you can, for example, take the K group, and you just take the direct sum of the K group of yes, finite extension of QP or function equal character, it doesn't. Yeah. Okay. JB smooth, yeah, like the first this part. But probably I need to take D and like derived categories. Yeah. D, this one? This here, D. Oh, yeah, this was good. Or maybe like in original branch, I would call homological duality of representation. And on the category representations, it will send a compact induction from some K to G to itself. Let's see. Huh? Yes. Thanks. HP. Or maybe let me just see. I can even just do less than or equal to B. Then usually you do this and then you do excitation and to get all the semi-orthogonal decomposition. What's the question? Compact objects. So that's basically a compact object there. So for example, it's compact objects, including, I mean, I'm not saying all of them, but the examples, including the compact induction from K to J, JBF, where K is prop P inside JB. For example, this is kind of, yeah. Why? What is 3? It's of course in general not true. Something compact generated category is always dualizable, but it still may not be itself in general. But I mean, one can sort of construct basically a natural pairing between these two categories in some explicit way, and there's something to check. Yeah. Huh? It's not that clear, but one thing you can do, if you agree there's a semi-orthogonal decomposition, you can do is you first using there's a self-dual here coming from the usual cohomological duality by, let's see, and then the whole category you can sort of express as the inductive limit of this whole thing, and then somehow there's some way to see. Okay. I mean, there's some not the additional structure. Yeah, I'm almost out of move this one. Yeah. Yes. So okay. So give me this. So what else I should say is okay. So maybe before I forget. Now at least I can make a conjecture, like write down the conjecture. Otherwise, before saying anything else, this is really one of the full sort of categorical version of local Langlands. Is this category is supposed to be equivalent to the category of maybe I take the compact objects and then the category of coherent shifts on this stack I introduced last time. Maybe, and here, because I'm doing this torsion coefficient, this is going to be coefficient over lambda, and one needs to add a little bit the cohomological condition here, which I ignore here. So it's supposed to be equivalence. And then the category of representation is embedded into here, for example. And this composition is supposed to be the functor I mentioned last time. Okay. So maybe I could see here also. Right. Smooth. Inside here. I should mention, this is something I really should say. So when B is 1, JB is just G itself. Okay. So I have 1. This composition is such that this should be this A I mentioned, for example. Okay. So what's sort of some evidence so suppose this is, okay, let's believe this is true. Although, of course, a priori, there's no reason to believe that. But let's see what first of all, of course, it will deduce such a fully faithful embedding, which is something, for example, can be tried to prove in various cases. Another thing that is if there's such thing is true, then there's literally some additional structure on the right-hand side, which is not a priori not obvious on the left-hand side. Namely, for any, let's say, space or stack or whatever, look, now this is kind of a really bad notation. But let me just see this curve, this category of perfect complexes. D omega. What is D is also used. You may quasi-coherent shift. I take the perfect object, but okay. Anyway, the perfect complexes. This is will act. So basically, it's just complex vector bundles. Let's say it will supposed to act on. Yeah. So here is basically complex vector bundles. And then if you have vector bundle, if a shift, the action is basically just by tensor product. So, and what are examples of vector bundles? So the typical, recall this stack itself is defined as some framed versions modulo the G hat. So every representation of G hat, algebraic representation of G hat, actually, you can think about this stacks really live over the classifying stack of BG hat. So, and the representation is basically a vector bundle here. You can pull back. You get, gives you a vector bundle called, let me write V tilde vector bundle. And therefore, each V2, so basically, so therefore, for every representation of a Langlands 2 group, there should be an action of the corresponding vector bundle on the coherent side. This is not a should be it's easy. It's a fact, but if there's such equivalence, such thing should also act on the constructible side, homomorphic side. So it turns out such thing do exist. So yeah, let me try to just sorry. Just this is actually, let's say V F go to V tensor F. Yeah, as over the structure shift. Yeah. Okay. So it turns out that this can be constructed unconditionally. This was really the key, sort of some strong evidence and some key result in Farks-Schultz's works. You can consider the following thing, the so-called the Heck stack, which is a kind of, you mimic the construction from the geometric Langlands. You consider two G bundles and a point. In fact, you can consider a bunch of points on this diff one. Let's see. Basically, an effective divisor of degree 1 on the Farks-Fontaine curve. Then it admits two map from Bang G, but just remember, maybe just write, yeah, sorry, not yet. And the modification, right? A modification, I don't know, at of these two bundles, which sort of, you know, in the function field case, this was spread out in quite in details in, you know, some lectures, and then you can basically, because it's really a curve, can do this. It's exactly the same form. And then you have this map to this times function. In fact, I can even, let's see, because of time, let's even forget this the projection to this factor. Maybe that's another good idea. Let's keep it. Yeah, let's keep it. Yeah. Okay. Then let's sort of, you know, very quickly outlined by Cong in her work, in her lectures. There's sort of some way to attach. Let's see. Suppose G split for simplicity. Split. H is just this is just remember E1, and this remember this point and the E2. Split for simplicity. So it turns out that there's a natural, the so-called geometric Stataki provides you a natural functor from the category representation of G hat to the category to some shifts on this Heck stack. I think. It's sort of unfortunately not possible to explain this concrete construction, but it's just some shift on it. And then one can define, once you have such thing, then one can define the so-called Heck operators from, which is defined as P H upper star of P times H lower star of let me write it this way. Tensor with S of B from shifts on Bang G to shifts from G times div 1. So one can define such thing. By the way, this guy is really by definition, it's a symmetrical monoidal category, because actually one can do the Kang extension in the category of symmetrical monoidal categories. So such thing makes sense. Okay, and then you can further restrict this just to Bang. I mean, I can't remember. This is you write it as like spot. This is like a spotty F modulo the Frobenius. So then you can just restrict to this point, and you get really, let's see, d bang G to d bang G, something like that. And that's operator suppose, and I mean, okay, so this is a sort of a construction, and then maybe the final word I would say is that construction actually defines should be correspond to just if there's such equivalence, it should be this correspond to tensor with this vector bundle. So I think my time is over. Stop here.